We just learned what and why number systems are by examining the number system we are most familiar with, the decimal number system. In this section, we're going to expand our understanding to two more number systems, the binary and the hexadecimal number systems. But before we do that, let's recap what we learned about the decimal number system. We learned the decimal number system is a base 10 number system. Therefore, digits may take on any value between 0 and 9 inclusive. And a digit is simply that value multiplied by 10 raised to a certain power, starting at 10 to the 0th. For instance, the number 111 is a 3-digit decimal number that represents 1 times 10 to the second plus 1 times 10 to the first plus 1 times 10 to the 0th. If we understand how our decimal number system works, then we can just as well understand how binary and hexadecimal number systems work. The binary number system is a base 2 number system. This means its digits can only take on two values, 0 or 1. And rather than each digit corresponding to 10 raised to a certain power, they correspond to 2 raised to a certain power. This means that our number 111 in a binary number system represents 1 times 2 to the second plus 1 times 2 to the first plus 1 times 2 to the 0th. And this pattern continues on into hexadecimal. Hexadecimal is, of course, not base 2 or base 10, but it's base 16. So its digits can take on one of 16 values, but we run out of numbers to represent these values, so we resort to letters. Therefore, hexadecimal digits range from 0 to F inclusive, and each digit is that value multiplied by 16 to a certain power. So looking at our number 111 through a hexadecimal lens, we now see that it represents 1 times 16 to the second power plus 1 times 16 to the first power plus 1 times 16 to the 0th power. But 111 in decimal is really a different value than 111 in binary or 111 in hexadecimal. So what is the decimal number 111 in binary and hexadecimal? Let's begin with binary, and let's begin by answering the question, how many binary digits do we need? Well, our first binary digit equates to either 0 or 1 times 2 to the 0th, so its maximum value is 1. The maximum value of our second digit is 2. The maximum value of our third digit is 4. Notice too that just like in our decimal number system, the sum of the previous digits equals 1 less than the leftmost digit. If we keep going, eventually we add a digit whose maximum greatest value is greater than our number altogether. That is our indication that we needn't add any more digits. In this case, the 8th digit, which equates to 2 to the 7th power, is greater than our decimal number we want to convert to binary. So we know our binary number will be 7 digits long. Now that we know how many digits we need, we can go ahead and convert our decimal number into a binary number, and we begin with the most significant digit, 2 to the 6th power. 111 divided by 1 times 2 to the 6th gives us a remainder of 47. 47 divided by 2 to the 5th gives us a remainder of 15. 2 to the 4th equals 16, which is greater than 15, so we know we need 0 times 2 to the 4th. 15 divided by 1 times 2 to the 3rd gives us a remainder of 7. 7 divided by 1 times 2 to the 2nd gives us a remainder of 3. 3 divided by 1 times 2 to the 1st gives us a remainder of 1. And finally, 1 divided by 1 times 2 to the 0th gives us a remainder of 0. So we've just calculated that the decimal number 111 is equal to the binary number 1101111. Now let's convert this number to hexadecimal. How in the heck might we do that? Well, remember that binary is base 2 and hexadecimal is base 16. 16 is the same as 2 to the 4th, right? So doesn't that mean that for every 4 binary digits, we will need 1 hexadecimal digit? Yes it does. And to help us out, let's rewrite our binary digit to better visualize that relationship. Now we can see that our binary number 01101111 is equal to a 2-digit hexadecimal number. This is possible because any hexadecimal digit can take on one of 16 values between 0 and F. A 4-digit binary number has exactly 16 possible combinations between 0000 and 1111. This means we can directly convert 4 binary digits into 1 hexadecimal digit. So, 1 times 2 to the 6th plus 1 times 2 to the 5th is equal to 6 times 16 to the 1st, and 1 times 2 to the 3rd plus 1 times 2 to the 2nd plus 1 times 2 to the 1st plus 1 times 2 to the 0th is equal to f times 16 to the 0th. So our hexadecimal number is 6f. And with that, congratulations is in order because we've just learned binary and hexadecimal number systems, and we calculated that 111 in decimal is equal to 1101111 in binary and 6f in hexadecimal.